Okay. So the last minute or two of the previous lecture was cut off. For those of you who didn't come today, that's why you should come. Okay. So what I want to do now is I want to talk about some other more elementary properties of the Fibonacci numbers. So this is called the Fibonacci quilt. And something very similar to this is done by people who quilt. Any quilters here? Do you know, like, I think it's called the log quilt? Yep. So it turns out there's many different ways to view the Fibonacci numbers, and different ways of defining them give rise to different properties and different questions. And so we know for the Fibonacci's that fn is equal to fn minus 1 plus fn minus 2. So what we have now is the following. Fn is fn minus 1 plus fn minus 2. And I'm going to define my sequence as 1, 1, 2, 3, 5, 8, dot, 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 dot. So I'm going to start off with 2 1s. Later I will be furious at starting with 2 1s, but for now I really like it. It's a little bit hard to see, but what I have here is I have different blocks. And so here, this is a 1 by 1 square, a 1 by 1 square, a 2 by 2, a 3 by 3, a 5 by 5, an 8 by 8, a 13 by 13, a 21 by 21, a 34 by 34. The next one is going to be 55. And so what's going on? So we start off with a 1 by 1 square. And now what I want to do is I want to make rectangles. And so the next thing I can do, let me just try to make sure I spiral in the same way, is, well, if I'm going to put squares down, the only square I can put in is another 1 by 1. Now I have a 2 by 1 rectangle. So what's the only square I can put in? A 2 by 2. Now I have a 2 by 3 square. What square can I put in? 3 by 3. Now I have a 3 by 5 square.
That's the funhouse square.
I think they're teasing you about your drawing.
You think? You can't make a more definitive statement? This sounds like certain press conferences I've heard where it could be pressure. No.
Objects are not as they appear, right?
5.
All right. The next one is going to be 5.
That's right.
Anybody ever watch the old Zorro movies? This was a Zorro and Son. This was a really old one. So the son comes back from school, and the father's eager to see what the son has learned. And so the son takes out his sword, and very beautifully etches out a Z and shows his father with pride. And the father goes, "It's a beautiful Z, my son, but you'd be dead. You got to get in, make your Z, and get out." And so while the artwork may not be exactly as you would like for squares and whatnot, we have to leave early. Now, if you guys want to stay all the way till 3 o'clock today, I will happily take out rulers and make beautiful illustrations. And so the next one, 8 by 8.
That's perfect.
Thank you. Next one. Yeah, I mean, at this point I don't care anymore. Next one is. So I'll leave it as something for you to ponder as to why it's going to fill out like that with the Fibonacci numbers. But in some sense, this is an induction. Here's F1. Here's F2. This is the length of this is F1 plus F2. And now the length of this is F2 plus F1. That's F3. The length of this is F3 plus F2. That's F4. The length of this is F3 plus F4. That's F5. So you can see the Fibonacci pattern. Now the difference between this and the log quilt is I think the log quilt you would just do this where these would just be one unit. And then it would look something like this. And then you would keep going. And so this is a famous quilting pattern. So in terms of things you can show, it's related, except now we're compressing things in directions. So this is a really nice way for the Fibonacci numbers. It spirals out. It spirals out, and it's going to fill the whole plane. So it's space filling. So there's not that many things that will fit together perfectly. So as you go further and further out, now, do people here have calculators? All right. All right. What's 1 squared plus 1 squared? You might be able to do this in your head. Plus 2 squared, plus 3 squared, plus 5 squared. So this is 2, 4, 9, so 10, 14, 15, plus 25 is 40. Any thoughts as to how else I could write 40? There's lots of ways. 5 times 8.
4 times 10.
No. So let's do one more. 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared. Well, right, because if it's 169,
104.
It's 104. Because I had 40 up to here, and now I'm adding 64. So it's got to be 104. And 104 is going to be 8 times 13. So how many of you have ever seen this property before of the Fibonacci's? Okay, Arthur Benjamin at Harvey Mudd has a nice TED video on this. So this is a very famous property. What would you conjecture if I did 1 squared plus 1 squared plus 2 squared plus fn squared? Fn times fn plus 1. And so one of the things is to lead students to certain patterns and see if they can predict, and once they have their prediction, if they can prove. So there's lots of different proofs of this. One of my favorites is just holding this up. We talked about units in the first day. Remember, trying to tie everything together. I don't know that many things, so I have to constantly keep using the same thing. Area has units of meters squared. It's area. When you look at the squares of the Fibonacci's, think of areas. Well, if I'm squaring them and I'm thinking of areas, they're tiling the plane like this. And so there's my rectangle. And so if I look at the sum of the first squares, I now have this rectangle here. There are 2 ways to calculate the area of the rectangle. One is the way we've been trained, length times width. Right? What's the length? The length is fn plus 1. The width is fn. The other way is, well, I've divided into a bunch of rectangles, into a bunch of squares. Let's just take the area of each square. What's the area of the square? Side squared. And so this is a proof that the sum of the squares of the first n Fibonacci numbers is the nth times the n plus first Fibonacci number. And so it's a really nice geometric proof. We could prove this using Benet's formula. I actually want to be invited back next year, so I'm not going to lecture on doing it that way. But if you have a troublemaking student, and you want to just, it's a great exercise to give them. Or a guy else, But what's really going on geometrically is think about how things piece together. What does it mean to talk about squares of Fibonacci numbers? Now again, the Fibonacci number is just a number. But if I assign units to it, it seems reasonable that if I want to sum squares, I would want some formula involving a product of 2 terms. And then what kind of formula would I want? So if you just try to give students a way to guess and say, look, we're talking about areas, so try to find a formula for this involving a product of 2 Fibonacci numbers. And have them play with this a little bit and have them actually predict the formula and then have them try to prove it. This is not an easy problem, but in terms of trying to help somebody think like a mathematician, take a pattern, take some data, make some guesses. This fits beautifully now in with the Pythagoras unit of trying to think about dimension, how this all ties together. And then they have the satisfaction of they've come up with the formula themselves. They haven't been given it. They've discovered it for themselves. So again, there's lots of cool properties of the Fibonacci numbers. There's lots of ways to prove them. This is one of my favorites. My daughter and I, so how many people have done fuse beating? So how many? Yeah, I was going to say it's a lot of beads.
That didn't get knocked on the floor.
No. Oh, sorry.
Did you do it in sets?
Well, no, we actually bought
even the squares are beads. Okay.
Yeah, oh yeah, yeah, yeah. Oh yeah. No, no, no. This is here. Melted beads. Yes. Ironed it. Yes.
Gotta use wax paper.
Got to use wax paper. But so we had a couple of big yellow squares that could fit together, and it took us 4 yellow squares to do this. And we had to go down a little bit on the ones down here. There's a danger of not having things connected. And then to get the next level, my daughter wanted to go 1 level deeper. And I'm calculating the budget cost of going 1 level deeper and the difficulty of actually ironing it. And so just ironing something of this size.
Get wider than the ironing board.
Yeah. Well, I mean, that's not a big deal, but just, things staying stable enough to iron it well. But just trying to find fun things to just bring in. My students like stuff like this. They've made fuse beads as well with us. And just, nice activities. You can see the spiral. Lots of great stuff in something like this.
Can you get away with paper?
I'm sorry?
Can you get away with paper that?
Oh, yeah. Oh, sorry. This is being recorded, so.
Like the leg.
Oh, sorry.
Sorry. What's the 34?
So the length of not the length of the diagonal, the length of the sides. So this
Oh, I see. So you've
right,
gone beyond.
right. So this is the 8, 13, 21, 34. Did not have the ability to do the smaller numbers, but we're big Red Sox fans, and so we had to get up to 34.
Maybe show her the spiral.
Sure.
board.
Yeah.
Because they're straight diagonal.
Right. And so I'm trying to think. So
You're using parchment paper instead of wax paper. You've got the artisanal beads, right?
right. So the spiral would be going like this.
What's the thing that's similar where you start off with right triangle, 1 by 1, so you get a root 2 hypotenuse. Now your next triangle is built root 2 by root 2, and the spirals out like that.
The hypotenuse keeps becoming a leg.
Yeah, yeah. But does that have ties into the? I mean, I understand the connection between this and that right there. I mean, you see the spiral pattern and that also.
Okay. So you start off with a right triangle.
So you start out with like a 1 by 1 right triangle. So
Right.
the hypotenuse is going to become root 2 on that.
And then you do a root 2 triangle.
Now that hypotenuse becomes the leg of a new right triangle. That's root 2 by root 2.
Oh, great. This is not going to be stuck for the rest of the day. And then this will become a 2.
And then
just
that
the
becomes a
spiral
leg.
off.
And then that spirals out.
Actually, yeah.
So the pizza's here, so we'll stop in just a second. This could be related to continued fractions. The golden mean phi 1 plus root 5 over 2, and then square root of 2, they both have very interesting continued fraction expansions. And that's another nice way of representing things. And this might be called the silver ratio. I would have to check.
Gold.
No, it turns out the golden mean, the golden ratio in some sense is the most irrational number. If you want to try to approximate an irrational number with rationals, this is the hardest one to do. And the way we measure how good of an approximation is we look at a rational and we want to make this small. Well, clearly, if I make q very, very large, my approximation is going to become very, very small. So I want to somehow measure how close this is, as a function of q. If it's really small, but q is really large, that's not so good. And so there's ways to quantify exactly how well we can do. All right, so this is a good time to just stop for a minute and get some pizza.